So in today's lecture video, we will be learning about the Lorentz transformations. In the previous lecture, we have discussed the Galilean transformation equations. These equations relate the coordinates x, y, z of a point in frame of reference S to the coordinates x prime, y prime, z prime of a point in a second frame of reference S prime. This transformation also assumes that t is equal to t prime. And we have also seen that this transformation is valid only in the limit when u approaches 0 or when u is much less than the speed of light. So in this lecture video, we will derive more general transformations that are consistent with the principle of relativity. So again, we have this two inertial frames of reference. So this is S, and then this is inertial frame of reference S prime. So S prime is moving at the speed u with respect to this frame of reference. So the question is, when an event occurs at point x, y, z at time t, as observed in a frame of reference S or O, what are the coordinates x prime, y prime, z prime, and time t prime of the event as observed in a second frame O prime or S prime, moving relative to O or S with constant speed in the positive x direction? So take note that for take note that the length is contracted and the time is dilated in, as seen by the observer in O or in S. So we have this one, x prime equals x minus ut divided by the square root of 1 minus u squared over c squared, where 1 over the square root of 1 minus u squared over c squared is just equal to gamma. So it can be written as gamma multiplied by x minus ut. While for y and z prime, y prime is just equal to y and z prime is equal to z, since our s prime is moving only along the x-axis. And for the time t prime, we have this equation. So t minus ux divided by c squared over the square root of 1 minus u squared over c squared, which is equal to gamma. So this factor here, 1 over the square root of 1 minus u squared over c squared is just equal to gamma multiplied by the numerator. So let us derive this transformation. Now let us start with the coordinate x prime. The coordinate x prime is the proper length in S prime. So x prime is the proper length in S prime. So in S, it is contracted by this. So as seen by the observer in S, we have x equals x prime over gamma, where of course gamma is equal to 1 over the square root of 1 minus u squared over c squared. Thus, instead of the Galilean transformation, so recall that the Galilean transformation for x prime is just x minus x prime is equal to x minus u t, or we can write x equals x prime plus ut. We have x equals x prime over gamma plus ut. Taking into account the contracted length as seen by the observer in S. So we can therefore write x is equal to x prime multiplied by 1 over gamma, where 1 over gamma is just the reciprocal of this expression. So we have 1 over gamma is equal to the square root of 1 minus u squared over c squared. So this is equal to x prime multiplied by 1 minus u squared over c squared plus u times t. And then solving for x prime, we have this equation. X prime is equal to x minus ut over the square root of 1 minus u squared over c squared. Or we can write this as x prime is equal to gamma. So the whole thing here, 1 over the square root of 1 minus u squared over c squared is just equal to gamma, multiplied by the numerator, which is x minus ut. So this equation is now the Lorentz transformation for the coordinate x from S to S prime. Okay, so to relate the coordinates from S prime to S, we just have to apply these steps. This has been discussed in the previous lecture video. So step 1, replace u with minus u. And then step 2, replace the unprimed coordinates with the unprimed. So in the previous derivation, we have obtained x is equal to x prime is equal to gamma times x minus ut. So this is from S to S prime. So to get S prime to S, we have x is equal to gamma multiplied by x prime plus u multiplied by t prime. Okay, so this is the coordinate transformation along the x relating S prime to S. Now take note that there will be no changes for the coordinate perpendicular to the relative motion of the frames of references. So we have y prime is equal to y and z prime is just equal to z. So in the same way, we have y is just equal to y prime and z is equal to z prime. Now, how do we go about the Lorentz transformation for time? So to derive the Lorentz transformation for time, we start with this one. X is equal to gamma multiplied by x prime plus u t prime. Okay, and then we solve for t prime. Solving for t prime, we have to multiply both sides by gamma. So we have x over gamma is equal to x prime plus ut prime. And then we subtract both sides by x prime. So we have x over gamma minus x prime is equal to u times t prime. And then we divide both sides by u so that we have x over gamma minus x prime multiplied by 1 over u is equal to t prime. Okay, so t prime is equal to, we have x over u times gamma minus x prime over u. Now take note that in the previous derivation, we have obtained this. X prime is equal to gamma times x minus u times t. So we have to eliminate x prime so that what will be left will be x. So we have from here, from this equation, we substitute x prime. So we have t prime is equal to x minus u times gamma minus, substituting, we have gamma x minus ut divided by u. Okay, and then we take out gamma, factor out gamma. So we have t prime is equal to gamma multiplied by x over this one, the denominator will become u times gamma squared minus, so this gamma term here has been factored out, so what is left is x minus ut over u, or we have gamma multiplied by x minus u gamma squared, this is gamma squared, minus x over u minus, or this is plus t, since we have a u in the numerator and then we have u in the denominator. And then the next thing is to factor out x. So we copy our expression. We have t prime is equal to gamma multiplied by x minus gamma squared u minus x minus u plus t. And then we factor out x here so that we have gamma multiplied by x 1 over u times gamma squared minus 1 over u plus t. Okay, now take note that gamma squared is just equal to 1 over the square root of 1 minus u squared over c squared squared. So this is equal to 1 over 1 minus u squared over c squared, or we can write this further as 1 over, we have c squared minus u squared. So we have 1 over c squared minus u squared over c squared, or we can further write this as c squared over c squared minus u squared. Okay, so we substitute this into our equation. Okay, so we have t prime is equal to gamma multiplied by x. We have inside the parenthesis, we can actually write u times gamma squared, and then we have 1 minus gamma squared. Okay, so take note that this term here is equal to this one. So we get the common factor or the least common denominator, and then we have 1 minus gamma squared over u times gamma squared plus t. Okay, and then we substitute our expression for gamma squared into this. So we have t prime is equal to gamma multiplied by x. And then we have 1 minus our gamma squared is c squared over c squared minus u squared divided by u multiplied by c squared over c squared minus u squared. We have plus t. Okay, and then we simplify. We have gamma multiplied by x. We have in the numerator we have this one, c squared minus u squared. So we have c squared minus u squared, and then we have minus c squared. And then in the denominator, we have u c squared over c squared minus u squared plus t. We further simplify. So, Kinesha, this term here, c squared minus c squared. And then we have here the denominator c squared minus u squared. So this can be written as gamma times x. We have negative u squared divided by c squared minus u squared multiplied by the reciprocal of the denominator, which is c squared minus u squared over uc squared plus t. So we can cancel this. We have gamma x, and we can cancel one u here because we have a u in the denominator. Negative u over c squared. Yeah, so this is the only thing that is left, plus t. For this is equal to gamma multiplied by t minus ux over c squared. So this is now our t prime. Okay, so let me rewrite. So we have t prime is equal to gamma multiplied by t minus ux over c squared. And applying our technique to find t, so we have t is equal to gamma multiplied by t prime plus u x prime over c squared. Okay, so this is for relating s to s prime, and then this one is s prime to s. Now we compare the classical and relativistic transformation. So we have here the list of the Lorentz transformation as compared to the Galilean transformation. So as you can see, we have this correction factor gamma, which is equal to 1 over the square root of 1 minus u squared over c squared. Now, if u is much lesser compared to the speed of light, then these equations will be reduced to the Galilean transformation equations. So this is also the coordinate transformation relating s prime coordinates to s. Examples will follow in the next video. Thank you for watching.